Let's start with our introduction. To begin, let's briefly introduce the concept. Engineering and biological systems often reflect each other in both structure and function. In our cases, mechanical system and the musculoskeletal system are strongly linked. And understanding this connection is essential in biomedical engineering. This parallel help engineer develop devices that assist, support, or even replace body function. Let's continue with our background studies. Mechanical systems use parts like levers, gears, and joints to create movement. And our body does something very similar. Musculoskeletal system use bone, muscle, and tendons to support motion and stability. These similarities are not just interesting, they are essential in biomedical design. They allow engineers to build devices like prosthetic and orthotics to imitate how the body moves and functions in daily life. The main goal of this project is to explore the relationship between mechanical system and the musculoskeletal system. We will compare how both systems work, identify key components, and examine a biomedical device inspired by mechanical design. This encourages us to think across disciplines, combining engineering principles with medical needs, especially in developing devices that restore movement and improve rehabilitation. Our scope includes comparison of both systems. A deeper look at a device like mechanical prosthetic limb, we will analyze how it works, how it's built, and how it mimics human movement. This topic is highly relevant in biomedical engineering because it's shown how mechanical knowledge directly improves healthcare.
And today I'll be talking about both mechanical systems and musculoskeletal systems. So starting off with mechanical systems actually they convert energy into any kind of a movement. So energies can be found in the form of hydraulic or pneumatic energies, and they'll be converted into any kind of a movement. So mechanical system is found mainly in any kind of a place where there are motors, there are stuffs that moves, such as any kind of industrial spaces, transportation, and so on. So the development of mechanical systems aids in any kind of a robotic development that moves, such as robotics and prosthetics, which helps in biomedical engineering. Current trends for mechanical systems include embedded systems and material sciences. Moving on to the musculoskeletal systems. Musculoskeletal systems, as what we've studied before, it has over 600 muscles and 206 bones. We also have cartilages, tendons, and joints, where joints allow movements in different angles and tendons attach muscle to bone. So the musculoskeletal system is mainly functional for us as a structural support, so it enhances our posture, maintains stability, and to absorb shock. So the contraction and relaxation of muscles such as actin and myosins produce movement. This is exactly like how gas and bearings helps movement in mechanical systems. Next, we're going to talk about a simple comparison between the engineering part and the biological part of the system. Next, so the first one is about the actuation and energy, where we talk about what exactly is used to begin and initiate the process of movement. So for the engineering part, which is mechanical system part, we have actuators, like hydraulic actuators. They will initiate the process of movement. While for the biological part, for the musculoskeletal part, ATP is involved in the actuation process. It is converted to a mechanical energy, which will initiate movement. Next is transmission and structure. So maybe we'll be talking about what exactly makes up the whole system and what exactly helps to transmit information in the system. For the engineering part, we have gas and bearings and brakes and so on to transmit information throughout the system, but they wear off over time. But for the biological part, which is the musculoskeletal part, we have the tendons and ligaments and joints. They transmit information between themselves during movements, but they won't wear off. Lastly is controls and feedback, like what exactly will be used in the systems to obtain any kind of information and for the feedback. For the mechanical aspect, we have sensors and controllers, which will be controlled by us humans because they can't be controlled by robots because they don't have their own thinking skills. While for the biological systems, we have receptors and feedbacks, and they are voluntary. They do it by themselves. They don't really need anybody to operate it because they can self-operate. Moving on, we're gonna discuss about the key components and organs that are involved in both of the systems. So for the first one is actuators and skeletal muscles. So the function of actuators and skeletal muscles is they produce force. Second is for frames and bones. Frames for the mechanical part and bones for musculoskeletal part. They provide structural support for the system. Synovial joints for the biological system and normal joints for the mechanical system. Joints, they enable motion, they absorb shock, and they reduce friction, which would kind of reduce the wear and tear. Next, cables and tendons, they will help as a medium to transmit force and informations. Support rods for mechanical and ligaments for biological is also important to stabilize the joints and to limit movement, which avoids excessive movements. Lastly is the control system for mechanical and nervous system for biological systems. They interpret the inputs that they get and they regulate actions, like they provide information on what should the feedback and the action should be. Lastly is for the diagrammatic comparison, where we compare the flow of information in both mechanical and biological, which is musculoskeletal systems. So for the mechanical system, we begin with a power supply. Since it's mechanical, it's motor robotic, we begin with power supply. Moving on to the actuator, which is the motor, which will produce information. Next we have gas and bearings and loads, which will keep on working in order to produce the movement. And then finally we have the movement. While for the musculoskeletal systems, we begin the process with energy in the form of ATP. So ATP, it allows muscle contractions. So muscle contractions, specifically actin and myosin, will activate tendons and ligaments and the information.
A robotic rehabilitation exoskeleton is a wearable electromechanical device designed to assist or restore movement in people with motor impairments. In my mix, the musculoskeletal system using sensors, motors, and control system to support working early movement, helping patients recover strength and mobility more effectively. A robotic rehabilitation exoskeleton functions by detecting the user's intention to move, often through biosignals such as electromyography (EMG), or by following pre-programmed movement patterns. Once an input is received, actuators are activated to produce joint motion that replicates natural human movement. This process supports motor learning, muscle reconditioning, and neuroplastic recovery, making it highly effective in rehabilitation therapy. The exoskeleton is built with several core components: a structural frame made of lightweight materials, actuators that generate motion, and joints that mimic the movement of knees or elbows. Sensors such as EMG, gyroscope, and force sensors gather data on movement and posture. A central control unit processes this input and controls the actuators accordingly. Finally, the system is powered by rechargeable battery pack to allow mobility and consistent performance. The system begins with input from the user, such as EMG signals from muscles or a manual button press. Sensors, like EMG motion of force sensors, detect movement and intent. The signals are processed by a microcontroller, which filters noise and interprets the data. A control algorithm then calculates how the motors should move. The motor driver amplifies the signal and powers the actuators, which generate joint movement. Finally, feedback sensors monitor actual motion and send information back to the controller to ensure accurate, smooth, and safe adjustment in real time. Robotic rehabilitation exoskeletons are now widely used in clinical settings to support recovery in patients with neurological and musculoskeletal impairments. They deliver repetitive, assistive movement that are vital for stimulating neuroplasticity and re-educating muscles. For example, in stroke rehabilitation, they help restore movement in weakened limbs by enabling repetitive walking patterns, which improve gait, symmetry, and mobility. In spinal cord injury case, exoskeletons provide mechanical support for walking and posture, allowing early ambulation that benefits circulation, muscle tone, and even mental well-being. Patients with neuromuscular disorder, such as cerebral palsy or multiple sclerosis, also gain strength, coordination and reduce risk of complications like joint constructures. Finally, in orthopedic rehabilitation, especially after surgeries like knee or hip replacement, exoskeletons aid in regaining range of motion and muscle strength, leading to faster and safer
Next, we move to
recovery.
the recent innovation in musculoskeletal system. Advancement in technology have been having an impact on the musculoskeletal system, which lead us to help in diagnosis and rehabilitation. Innovation that exists nowadays encompass various fields. One of the recent innovation that has an impact on technology is 3D bioprinting and additive manufacturing. This innovation allows the creation of the patient-specific scaffold that mimic the natural extracellular matrix of bone, cartilage, and muscle. And this scaffold can be laden with cell and bioactive molecules to promote tissue regeneration. Besides, in the aspect of tissue engineering and regenerative medicine, organ-on-a-chip and microphysiological systems of innovation have been developed. These miniature models of human organs and tissue have been made based on the microfluidics technology. This successful technology is an in vitro human microphysiological system that can summarize the organ level and even organism level function. Sophisticated robotic arms, like the cooling orthopedic biomechanic robotic arm COBRA, are advanced systems that can precisely simulate complex human joint movement, allowing and for incredibly accurate testing of orthopedic implants. Beyond just testing, COBRA also developed new surgical techniques lead to better outcome for patients. Advanced medical imaging contributes significantly, offering incredibly detailed insight into patient health. Combining the power of imaging modalities like X-ray, MRI, and CT scan, and ultrasound with sophisticated image processing and analysis techniques, especially those powered by AI, yield a much clearer picture of musculoskeletal condition. Next, we move to the part application of mechanical system in biomedical devices. One of the mechanical systems that is applied to the musculoskeletal system is orthopedic implants. Implants are designed to withstand the immense and repetitive forces in daily life activities such as walking, running, and jumping. Mechanical engineers use principles of stress analysis, fatigue, and fracture mechanics to select appropriate materials. Next, prosthetics are complex mechanical systems since they are involved a few aspects like joint mechanism, socket design, and material weight. In joint mechanisms, prosthetic knees often incorporate mechanical linkage and springs to mimic the natural gait and absorb shock between the patient's body and prosthetics. The loads that have been applied need to distribute evenly to secure suspension and allow for efficient force transmissions. Lightweight and high-strength materials like carbon fiber and aluminium alloys are used in the prosthetic limbs to minimize the burden on users while using them. Other applications are rehabilitation devices. Therapeutic exercise machines like treadmills and stationary bikes are used to provide control resistance and support muscle strength and endurance training. In advanced mechanical systems, exoskeletons, wearable robotics are being used by patients as power assistant for movement, to aid training, or to support weakened limbs.
Next, let's move to traditional versus modern medical devices. Due to significant advancements, technology has been improved rapidly. It shows that modern technologies such as artificial intelligence, Internet of Things, 3D printing demonstrates how innovation can increase efficiency. For future recommendations, developers suggested to include virtual reality to practice functional movements in simulated real-world scenarios, which also promotes motor skills. Second one is implantable and biodegradable system for bones and joints fracture to enhance coordination with only minimal surgical procedures. So in conclusion, from studying both mechanical and musculoskeletal similarities is a good approach to invent new devices with correct principle of muscle movement and strong foundation to develop an accurate and reliable devices.